Okay, so this example here, let's find the volume of the solid revolution using the shell method. You could use the disk method pretty easily because there's no gaps, there's no holes. You're not revolving it around something like this where there is a big hole in the middle of this volume. But let's practice the shell method. So what we want to do is we want to envision where these shells are and what kind of they look like. And so if we're revolving it about the y-axis, that means we are looking for a shell that looks sort of like this. There's one. Right? And then here's another one that's really wide, out here, really wide, but really stout. See that? So, and we're looking for a collection of everything in between there, and all the way to the very end here. So we have a really wide cylinder, but it's super short. So let's think about this, okay? So we know that the volume comes from 2 pi times some integral from some limits of integration, we'll get there, and then 2 pi r times h, and then d of something, okay? So we're revolving around the y-axis. Let's take a look at, this is where I like to start, the radius. Okay, what is the radius? Is the radius of these cylinders that we're envisioning, is it x or is it y?
X.
Yeah, it's in the x direction, you see that? So when we're revolving about the y-axis, the radius of that shell is going to be an x. So this r, okay, is actually going to be just plain old x. The height is going to be the difference between what? Between the top function, which is y equals what? 2, and the bottom function, which is y equals, now do we need to do this in y equals or x equals, I guess? Well, let's come back to that. Okay, so the height is going to be, these are the heights represented here. So obviously it's going to be the difference between the top function and the bottom function. Are we doing dx or dy? Yeah, and if you think about the radius in the x direction, okay, the width of this shell is very super narrow, but the width would be a differential of x, just a little bit more x, right? It's between, the radius and then just beyond the radius. That's the thickness of the shell. So this is going to be dx. So if the radius is in terms of x, this has to be dx. Okay, so what does that mean? Well, that means that the limits of integration have to be in that x direction as well. So we got to go from 0 to what? 0 to 2 or 0 to 3?
3.
Okay, so again, the dx, the differential of x, is going to go, and the radius, going to go from 0, really radius, to 3. So that should be 0 to 3. And so then we know that the functions that form the heights of the cylinders need to be in terms of x, because we're dx here. So this is right now x equals 3y over 2. They're just giving you an extra step. So we have to solve for y, right? So let's just show you the whole thing here, over 2. So that's 2x equals 3y. So that's going to be y equals 2/3 x. That look good? So we've got the height here is actually going to be y equals 2 minus the height of this lower function, which is going to be 2 minus 2/3 x. Okay? Are you with me so far? So we got to put this all together. Let's put this all together over here at red. So we got 2 pi. We have an integral, and we're going to go x direction from 0 to 3. And the x is going to be our radius, because we're revolving around the y-axis, so we don't have to add anything to the r. It's just going to be, the radius is just going to be whatever the x value is. That's going to be the radius of these cylinders, because the middle is at the y-axis. And then h, we said, was 2 minus 2/3 x, and all this integral with respect to x. Okay? So why don't I give you a second just to complete that and see if you get this answer of 6 pi.
Well, the answer is...
All right, so hopefully you had a chance to try that out here. You should get an answer of 6 pi, and this is sort of what you want to do in solving that, evaluating that integral. Any questions? Not for now. That's good. That's a good answer. Okay, you guys are good?